Welcome folks to the part 6 of this SwimMove course. In this course, we will talk about the homogeneous collections. So first of all, we'll introduce to the homogeneous collections. Then we'll understand how vectors and table works under the homogeneous collections. Alright, let's start with the introduction to the homogeneous collections. So what are the homogeneous collections? Those are a type of data structure where all the elements are of the same type. The term homogeneous comes from the Greek words for same and kind, signifying that all elements in the collection belong to the same kind of type. Here are a couple of key points of homogeneous collections. The first one is consistent data type. So since all elements in the collection are of the same type, you know what type of data to expect when you access the elements of the collection. This consistency can greatly simplify the coding and debugging process. The second one is efficiency. Homogeneous collections allow for certain optimizations because operations can be applied uniformly to all elements. This can result in a more efficient code executions. And in the context of the Move programming language, there are two types of the homogeneous collections: vectors and tables. A vector in Move is similar to those in other languages such as C++. It's a flexible way to manage a group of single type, which can be a specific type or a generic type. A table is a map-like collection that dynamically stores key value pairs. All keys and all values in a table must be of the same type. Homogeneous collections are a fundamental concept in many programming languages and are used in a variety of applications, from managing groups of data in a consistent and predictable way to performing operations on groups of elements efficiently. Okay, let's start talking about vectors. In computer science, a vector is a dynamic array or a resizable array. It's a type of data structure that can hold elements of a single type and can dynamically adjust its size as elements are added or removed. So let's say some properties of vectors in Move. The first one is a dynamic memory allocation. Unlike static arrays, vectors in Move can adjust the size during the program's runtime. This means you can add elements to a vector or remove elements from it as needed, without having to know the vector size at compile time. And the second one is the single type elements. All the elements in a vector are of the same type. This type can be a specific type, like an integer or a string, or it can be a generic type. And then followed by the basic operations. Vectors supports several operations, such as creating a new vector, adding an element to the end of the vector, or removing an element from the end of the vector, and getting the size of the vector. And lastly, it's homogeneity. While a vector defined within an generic type can accept objects of an arbitrary type, all objects in the collection still must be the same type. This means the collection is homogeneous. A vector is an important data structure in Move and other programming language due to its flexibility and efficiency for managing collection of data. A vector in Move shares many similarities with vectors in C++. Here are some comparisons. The first one is a dynamic size. So both Move and C++ vectors are dynamic arrays, meaning that they can change size at runtime. You can add elements or remove elements from both types of vectors as needed. The second one is homogeneous elements. Both types of vectors are homogeneous collections, meaning they can only contain elements of a single type. So for instance, a vector of integers can only contain integers. And as for accessing elements, in both Move and C++, you can access elements in a vector by their index. The first element is at index 0, and the second element is at index 1, and so on. Both move and C++ vectors handle memory allocation automatically. When you add an element to a vector and there's not enough space, the vector will automatically allocate more memory to accommodate the new element. As for the specific and generic types, both vectors can be of a specific type or a generic type. So for instance, in C++, you can have std vector integer, which can only contain integers, or a std vector t, which can contain elements of any type t. Similarly, in move, you can have a vector widget, which can only contain widget objects, or vector t, which can contain elements of any type t. However, it's important to know that even if a vector is of a generic type, it can only contain elements of the same type. For example, if you create a vector t and add an integer to it, you can only add more integers to the vector, not strings or any other type. And for the mutability, so this is where separates move and C++. In C++, once an object is added to a vector, you can still modify that object directly through the vector. However, in move, vectors are immutable. You can add or remove elements, but you cannot change an element that is already in the vector. Overall, while vectors in move and C++ share many similarities, the differences mainly stem from move's design as a language for safe and predictable programming on the blockchain. So this code defines a module called GameVector, which provides functionality for working with vectors of items in a game context. The item structure represents a generic item in the game. It serves as a placeholder for any specific item type that the game may have. And for the item vector, this is a specialized vector that can hold the item instance. It acts as a collection to store multiple item objects. As for the generic vector, this is a generic vector that can hold elements of any type T. It is a versatile data structure that can store any data type, not just the item instance. And the module provides the following functions. First is the create function. This function creates and returns a new empty generic vector that can hold elements of type T. It initializes the vector with an empty collection of T elements. Then we have add item function. This function adds an item of type T to the specified generic vector. It appends the item to the end of the vector. Then we have the remove item. So this function removes and returns the last item of type T from the generic vector. It effectively pops the last item from the vector. And also the getSize function. So this function returns the size of the given generic vector of type T. All those functions will provide a basic functionality to manage a generic vector in a game context. Game developers, therefore, can use this function to create, add, remove, and get the size of the vector containing any type of the game-related data. It offers flexibility and convenience in handling collections of elements in the game's logic. Okay, let's try to understand tables. So, in the context of move programming language, a table is a type of homogeneous collection that behaves like a map, storing key value pairs. However, it differs from the traditional map collections in the way it stores key and values. Here are some key points about a table in move. The first one is the dynamic storage. A table dynamically stores key value pairs. This means that the data is not stored within the table value itself, but is stored using Swiss object system. And second one is the handle system. The table structure acts as a handle into the object system, which is used to retrieve the keys and values. This means that the table itself does not contain the data, but it provides a way to access the data stored in the object system. And then we have homogeneous collection. Like other homogeneous collection, a table in move requires all keys and all values to be the same type. This can either be a specific type or generic type. After that is ability constraints. The key type of the table must have the ability constraint of copy, drop, and store. And the value type must have the ability constraint of store. This ensures that the key and values have specific abilities that allow them to be used effectively within the table. In summary, a table in Move is a powerful data structure and provides dynamic, type-safe storage of key value pairs, with the capability to enforce specific abilities on the keys and values it stores. This makes it a valuable tool for many kinds of programming tasks in the blockchain context, especially those requiring efficient, flexible, and type-safe data storage and retrieval. Okay, so in the Move programming language, a table can be considered as a form of map collection, but it has distinct characteristics that we have mentioned, which set it apart from the traditional map collection you might find in other programming language. And the first one is the storage. So traditional map collections usually store their key value pairs directly within the map, but in the table in Move, the keys and values are not stored with table values. Instead, they're stored using the Swiss object system. And the second one is the type constraints. Traditional map collections can often store heterogeneous data, meaning keys and values can be of the different types. However, in a table in Move, it is homogeneous collection, where all the keys and all values must be the same type. And finally is the ability constraints, like we mentioned. So, while tables in Move and traditional map collections both store key value pairs, the way they store the data, the type constraint they enforce, and the ability constraint in the case of tables in Move make them different from each other. So in the Move programming language, types can be associated with certain abilities that dedicate how they can be used. These abilities include copy, drop, and store. Let's break down these abilities in the context of the table. So for copy, this ability allows a value of the type to be duplicated. In the context of table, the keys must have this ability, meaning they can be copied. And drop will allow a value of the type to be discarded. For table, this also applies to the keys, indicating they can be discarded. Store allows a value of the type to be stored in the Swift storage. For the table, both keys and values must have this ability. So in summary, the key type in a table must have the copy, drop, and store abilities. And the value type must have the store ability. This means keys can be copied and discarded, and both keys and values can be stored in the Swift storage. This constraint ensures that the table can function correctly as a key value storage system. And this code defines a module called game table that provides structure to work with tables in a game context. The item table defines a table called item table with specific types for the key and value. In this case, both the key and value are type U8. And generic item table. So this structure defines a generic table called the generic item table, with generic types for the key and value. The phantom keyword indicates that the types K and V are only used for compile time table, checking and do not consume any memory at runtime. The copy, drop, and store traits specify the requirements for the types that can be used as keys and values in this table. This code provides function to interact with the generic table in a game context. The table is called generic item table and allows storing key value pairs with the generic keys and value types. So the create function will create a new empty generic item table with a specified key type K and value type V. It takes a mutable reference to the transaction context and returns a newly created generic item table. The function add will add a key value pair to the generic item table. It takes a mutable reference to the table, a key of the type key, and also a value of type V. The remove function will just remove the key value pair associated with a given key. And the borrow will borrows a mutable reference to the value associated with a given key K in the generic item table. The borrow mutable function basically just borrows a mutable reference to the value associated with the given key. And the contains function. This function will check if a value associated with the given key k exists in the table and returns a boolean indicating the result. Finally is the length function. So this function returns the size of the generic item table, which corresponds to the number of key value pairs it currently contains. And that's it. That's the lesson for the homogeneous collection. I hope you enjoyed it.